Okay, so welcome back, everybody. So let's pick back up with note 6 here, just a quick review here. So we're talking about transmission lines, and the general definition of a transmission line is two conductors running side by side, or maybe one inside the other one, but notice that in the z direction, the system does not change shape. It's two conductors, and the balanced or so-called differential mode, the usual mode that we prefer to operate in, is one where there's equal and opposite currents on the two conductors. There's a voltage drop between the two conductors and equal and opposite currents on the two conductors. Okay, and again, they can look like this, or they can look like this, planar transmission lines on the circuit board. Okay, but they all have one thing in common: two conductors. A conductor like this one that carries current in one direction, and the other one, in this case, it's really two, but an outer conductor, let's say, that carries current in the opposite direction. Okay, there's a general schematic. Remember the convention. Voltage plus on top, negative on the bottom. This is the z direction. So we say, for example, there's a signal generator over here that launches a wave. The wave is going to be going down the line in the z direction towards the receiver, let's say. And the reference direction for current is as shown here. I don't always draw this bottom one, but remember, it's understood equal and opposite currents. Okay. We have the four fundamental per unit length parameters that I introduced last time: C, L, R, G. And so a small little slice or piece of the line, if you blow it up, has this model. Okay. Now, I'm not sure if I mentioned this note last time, but let me just kind of mention it. This is my model that I'll start with today for deriving the differential equation, the telegrapher's equation. Now, it's possible to reorder the elements. Like, for example, why did I put these two series, the R and the L, on the left? Why didn't I put them on the right? I could. In some books, you'll see something even fancier where they cut these down by a factor of 2, and then they put half here and half over here. Now, I'm not going to go through the math, but maybe you can believe it, that no matter what I do there, in the limit, when delta z goes to 0, I get the same differential equation. So it doesn't matter, right? The important thing is you got series elements and you got parallel elements. R and L are in series, G and C are in parallel. Doesn't matter exactly how you rearrange them like that, as long as you maintain that. Okay. But the simplest model, in my opinion, is just to lump the two series one on the left and just put the parallel ones on the right. But other orders are possible. Okay. So anyway, this is our model. And the claim is it becomes exact in the limit when delta z approaches 0. And so the goal is to try to use the circuit model for a small piece of the transmission line and derive a fundamental set of differential equations that describe how voltage and current travel, or to use the fancy word, propagate on a transmission line. Because that's what we're after. You might have a signal generator over here. You might have some kind of receiver or load over here. And the signal generator is sending a signal down the line to the receiver, maybe on a coax, maybe on a microstrip line on your circuit board, whatever. And we want to know how that signal is traveling. Now, a little bit later, in note 7, we'll be also interested in knowing how a signal might reflect off a load if there's a load on the end. And there always is in practice, right? Practical receiver or something. Okay, and that gets into the concept of reflection coefficient, but we're not doing that in note 6. Okay. Anyway, I already talked about this. We derive everything for the coax, basically. So now we're up to here, the telegrapher's equations. That's the official name for the differential equations for the voltage and current on a transmission line, the telegrapher's equations. It goes back to the old telegraph. You know what that is from the old Western movies, right? One of the first types of transmission lines used for long distance communication, right? And famous people like the famous physicist, you may have heard of him, Lord Kelvin. I forgot what his real name is, William Thomson maybe, but anyway, we call him Lord Kelvin. So he was the first one to really study rigorously the mathematical solution of waves on a transmission line, back when they had the old telegraph, okay? And famous people like Oliver Heaviside got involved too and did some important contributions to transmission line theory, okay? But anyway, so the telegrapher's equations, as we'll see in a minute, are a fundamental set of differential equations that describe how voltage and current propagate, or in other words, travel on a line, transmission line. The derivation holds for any transmission line. I'll use this, the circuit model here, like I said, and this is the schematic, but it holds for any type of transmission line. The telegrapher's equations are exact once we take the limit, delta z goes to 0, and it's valid for any type of signal propagating on any type of transmission line. Okay. Now, there's one bit of bad news. We only have an exact solution for these differential equations in the time domain, when the transmission line is lossless, I'm going to derive the telegraph equations allowing for loss. That's the R and G elements. But when I solve the differential equation, I'm going to set them equal to 0 and assume it's a lossless line. Otherwise, there's no exact solution in the time domain. In the frequency domain, there is, but we're not there yet, right? We're all in the time domain right now. Okay. All right. So now the differential equations for voltage and current are coming just from the good old circuit equations, because that's what this is. It's like a circuit, the KVL and the KCL laws that we're all familiar with. So this is that little piece of the transmission line. The left is called Z, the right is called a little distance away, Z plus delta Z, and delta Z is going to get small in the limit, okay? Now remember, RL, GC are all per meter. So if I want this total value in ohms, it's R times delta Z, right? If I want this total inductance in Henry, that's L times delta Z, et cetera. Okay, that's why the delta Z is there, okay? So remember the labeling, plus minus for voltage, and the reference direction is on the top wire of the schematic. It's left to right. So notice this is called voltage ZT, because everything's a function of distance and time, right? V and ZT. Here it's called voltage at Z plus delta Z, right? T. Same thing for current, IZT, I of Z plus delta ZT. Now let's do the KVL. The KVL simply says this voltage plus or minus is equal to this voltage here plus minus plus what? What would circuit theory say? Plus the voltage drop across these two guys, plus here, minus here. So plus minus voltage across the resistor, plus minus voltage across the inductor. Okay, what's the voltage drop across the resistor? Simple Ohm's law, the current flowing through it times its resistance. What's the voltage drop here? Plus and minus across an inductor, total inductance times the derivative of this current with respect to time. Okay, that was simple. Now let's do the KCL. KCL says this current going on the left, that's this, is equal to this current coming out on the right, that's this, plus whatever current went down through these two elements. Now, what current is going down through these two elements? Well, going down through the resistor is the voltage across it. Now, we're not going to call it V of ZT, right? We're going to call it V of Z plus delta ZT, right? That's what it sees, right? So V of Z plus delta ZT times its conductance, G per meter, and then times delta Z, right? That's the total conductance of this element. And then what about the current going down through the capacitor? Total capacitance in farads times the derivative with respect to time of the voltage that it sees, which again is this right here on the right. So Z plus delta Z. Does that make sense? Okay, now the last step to get the differential equations is we just rearrange and then take the limit and then divide by delta Z and take the limit as delta Z gets small. It works the same way with both of them. Let's just do the top one, the KVL. So I'm going to take this one on the left, take it across the equal sign. So I'll have this term here minus this one. And then if I divide both sides by delta Z, I'll have this minus this over delta Z, and it's going to look like a derivative. Okay. Now these two guys here, I take across, so there'll be a minus sign. And when I divide by delta Z, the delta Z just goes away. So the first one gives me this. And do the same algebra on the current gives you this. Okay. Now, drawing back on our knowledge of calculus, I hope you agree that if I take this term on the left and I let delta Z get small, that's basically the derivative of voltage with respect to Z. Right? You're sampling at Z plus delta Z, and then minus sampling at Z, and then divided by the distance between. That's the definition of a derivative, right? As delta Z gets small. Now, to be precise, we call it the partial derivative of V with respect to Z, because remember, V is a function of two things, Z and T. So when I take the derivative with respect to Z, we should really call it partial derivative, right? The derivative with respect to Z, partial V with respect to Z. So that's what the left-hand side becomes. Now, on the right-hand side, well, this is nothing happens here. I just copied it down, minus R times I. Now, I'm not going to keep writing the argument everywhere, Z comma T. We understand everything's a function of Z and T. So for simplicity, I didn't keep writing it down here. And then minus L partial of I with respect to T. Okay, see that? Now, the second telegrapher's equation, this becomes partial of the current with respect to Z. minus GV. Now this one has Z plus delta Z, but don't let that bother you. Remember, delta Z is still going to 0, right? So there's no harm in just calling this Z, just like I did up here. It already has Z, right? So it doesn't really matter. So it's going to be minus GV minus C partial of V with respect to time. You see that? So there you go. Those are the two fundamental differential equations called the telegrapher's equations for how voltage and current travel or propagate on a transmission line. Our goal is, of course, to eventually solve them and see what happens to a signal. Okay. Now, when you have a signal coming out of like a generator going down a transmission line, the signal, if you will, consists of both current and voltage, right? It has both. Now, they're related, but we haven't talked about that yet. They're related by something called characteristic impedance, which we'll get to in a little bit. Don't worry about that yet. But the signal consists of both of them. But now notice this is a coupled set of differential equations. A mathematician would say this is a coupled set of first order partial differential equations. That's the official name of it. Now you can't just solve one by itself, because notice that V is in terms of I, but then this one says I is in terms of V, right? So they're coupled together. So you got to solve them as a pair. Okay. Well, now one thing you can do though is you can substitute one into the other one to eliminate one of the two, voltage or current, and get a differential equation for only voltage or only current, which I'll do in a second. Now, the price we have to pay is it becomes a second order differential equation. But it's still kind of nice because it only has just voltage or current in it. Okay? All right. Now, that's what I'm going to do right now. Here's the recipe. First step in the recipe. Take the derivative of the first telegrapher equation with respect to Z. The first one is here. So I'm taking the derivative of both sides with respect to Z. So this is going to convert on the left to second partial with respect to Z, right? This term, I'll have partial of I with respect to Z. This already has a time derivative. So I'll have time derivative and then Z derivative. Okay, so it becomes like this. Now, I'll do one thing. For this term right here, see, this says take time derivative first and then Z derivative. Calculus says you can switch the order as long as the derivatives are continuous. So I'm going to say Z derivative first and then time. Now, why is that helpful? Look what I have here and here, two places here and here. I have partial of I with respect to Z. But wait a minute, that's what the second telegrapher's equation gives me, right? Partial of I with respect to Z. And there it is one more time. So from the second telegrapher's equation right here, I can just substitute this right-hand side here in these two places here. So it becomes here and it becomes here. Okay. All right. Now notice when I did that, there's a time derivative here. So V got converted to derivative with respect to time. And then this already had a derivative of V with respect to time. So that got converted to second derivative with respect to time. Okay. Now there it is. It looks kind of messy, but as you can see, it only has V in it, no I. So we were successful. Now it's a second order differential equation because you see it's got a second order derivative with respect to Z and also with respect to T. Okay. Now here is sort of the final form of the equation. I've just rearranged it and collected terms a little bit. So I took everything across the equal sign. So it's everything equal to 0, right? So for example, I got this term right here. 2 minus signs is a plus, but then I took it across, so back to a minus sign, right? I collected everything in front of partial of V with respect to time. So that's going to be a term here, and it's also going to be this term here. And then I've got the second order time derivative that also, again, that got taken across. So there it is, final second order differential equation for voltage on the transmission line. Now, I'm not proving it here. You know, you're welcome to try it yourself, but the current obeys exactly the same differential equation. So I chose to eliminate current and solve for voltage. I could have done the other way around. And then I would have got a second order differential equation for the current, but it's exactly the same equation. And it's probably not surprising because when the signal goes down a line coming from like a function generator or signal generator, the signal consists of both. It has voltage and current. They propagate as a unit. That's what we call the signal. Why wouldn't they obey the same differential equation? Right? You can't really have voltage doing something different than the current. They're both going to travel at the same speed, et cetera, right? So it's not surprising, but again, if you want to prove it to yourself, I invite you to do it. Now, as I mentioned before, and I'm saying again here in the box, kind of the bad news, nobody, as far as I know, has ever been able to find an exact solution to this differential equation, right? Of course, you can do it numerically, of course. Of course, if you're willing to do it numerically, you can just go back to the first order differential equations, a couple set of differential equations, and solve them numerically too, right? But anyway, but there's no exact solution, analytical solution to this in the time domain, which is what we're doing right now. Now, on the other hand, the good news is that if I assume it's a lossless line, there's a simple exact solution. Now, lossless line, now remember, the loss comes from two things: R, which is the metal loss, the metal resistance of the line, and G, which is the conductance if the dielectric between the lines is lossy, right? Like the Teflon and the coax, if it has a loss in it, some kind of conductivity, right? So lossless means both R and G are zero. Perfect conducting wires, no loss in the wires. G is zero, perfect insulator between the wires. Okay, that's what a lossless line means. So you can see why that simplifies. This whole term is zero here. And since R and G are both zero, this whole term is gone, right? So all I have is these two final terms right here. So this simplifies down to this. Great simplification. Okay. Now we have a hope of solving that exactly. It's really, really simple. Okay. Now I already mentioned this last time. I proved it for the coax, but I asked you to believe it that's true for any transmission line. And that is for any transmission line, L times C, inductance per unit length times capacitance per unit length, is always equal to mu epsilon. This is mu and epsilon of that material, like in the coax. Usually mu is mu zero, of course, because Teflon is non-magnetic, right? But anyway, and speed of light in the material is 1 over the square root of mu epsilon. So LC is always then 1 over the speed of light squared, and the D subscript means speed of light in this material, in this dielectric material, like the Teflon. Not to be confused with the symbol C, which means speed of light in vacuum, right? Now, you might have a transmission line like the twin lead, which for all practical purposes is the conductors are in air, so CD would be equal to C. But for most transmission lines like coaxes, they're filled with insulating like Teflon, so CD is less, of course, right? In other words, epsilon is going to be epsilon 0 times epsilon R, in other words, right? Okay, so anyway, this can be written very simply as just 1 over speed of light squared. And that'll be the simplest final way I can leave the differential equation for the voltage. And it's called a wave equation because it's going to predict that the voltage travels as a wave on the transmission line. The signal travels down the line, just like a wave on water or a sound wave in air travels, right? It's a wave traveling down the line. The signal is traveling. It goes from point A to point B. It goes from the generator to the receiver. Okay. Anyway, so waves come out of it. It's called the wave equation. Now, there's two forms of the solution. And in just a minute, I'll just do some simple math to verify that this is a valid solution. But right now, I'm just going to show it to you. So I'm giving you two alternative forms of the solution. Okay. Now, notice that this one uses lowercase f and g. This one uses uppercase f and g, just to distinguish between the two of them. Okay. But anyway, when you see f, that's going to be the notation that means a wave traveling down the line in the positive z direction. Now, f is an arbitrary function because the transmission line theory doesn't know what shape of signal you're putting on the line, right? Your generator could be putting out a square pulse or a triangle wave or who knows what, right? The theory doesn't care. So f can be an arbitrary shape signal function. But here's the important thing. Z, the argument is z minus speed of light times time. So, and I'll give you more pretty pictures in a minute, but the physical interpretation is simple. Let's say at t equals 0, the voltage waveform has a shape f of z. It could be some rectangular pulse or something, right? Now, at a later time, y'all know what a plot does. If I say, f of z and then f of z minus something, what does that do to the plot? It just shifts it, right? So if you go to a later time, the plot is shifted by what? Speed of light, meters per second, times time in second, the meters it traveled. Makes perfect sense. The waveform hasn't changed shape on a lossless line. It's just moved at the speed of light. The conclusion, very simple. Now, what's the physical interpretation of a g function? Notice the plus sign here, which could be written as z minus c dt. Okay, the interpretation of that is the wave is just going in the backward direction, it's going in the negative z direction, right? As time gets more positive, this becomes bigger, and so it becomes z minus a larger negative number. So it's just a waveform that's not changing shape, and it's going in the backward direction. Okay, now once I put a load at the end of a transmission line, When I say an incident signal is hitting the load and reflecting off, now we can relate the wave going this way to the wave going this way, but that's not this set of nodes, okay? Right now, I'm just saying F and G are arbitrary functions. So a wave going one way, a wave going the other way, they can be anything you want. Now, an alternative notation is this here, where you use the capital F and the capital G, and it means the same thing, wave going in the positive Z direction, wave going in the negative Z direction. And this is, I'll use this notation when I want to emphasize that it's kind of like a function of time, but the time delay caused by distance over speed. I like to prefer this form here. I like to use this form when I want to kind of emphasize that I'm thinking of plotting, the function of voltage versus distance versus Z. Okay, and if I change time, there's a delay, right? But I'm plotting versus Z, whereas this is more convenient if I'm thinking of plotting versus time. But two alternative expressions, okay? Here's another fancy name for it, the D'Alembert solution for the mathematician that came up with it. But anyway, traveling waves. Again, important thing, F is a wave going in the positive Z direction, G is a wave going in the backward negative Z direction, okay? All right, so that's a solution. Now, this is what I just said a minute ago, but here it is. Again, form number one, although they're both mathematically equivalent, form one is more useful or more convenient when plotting voltage versus distance. And form two is a little bit more convenient, as we'll do later, when we plot voltage versus time, which is like what an oscilloscope would show. So if I want to think about what an oscilloscope is going to show at this point in the line or this point in the line, form number two is going to be more convenient. If I just want to visualize what the waveform looks like at any instant of time, in other words, a snapshot, as I call it, form number one is more convenient. Okay, I snuck this slide in this morning. This is, in case you're interested in this kind of mathematics, I'll just show you how the two forms are related. Okay, in other words, a lowercase fg, uppercase fg. How are they related? Okay, let's take this term. It works the same way for the f and g. Let's just take this one right here. So I'm looking at this term right here. F of z minus c dt. See, I just copied it down right here. Okay, now very simple math. Inside the parentheses, I just factored out minus CD. See that? So this is equivalent to this. I just factored out minus CD. And notice when I did that, the important argument that's left is T minus Z over CD. Ah, that's what I see here. You see that? So I'm going to say that's capital F of T minus Z over CD. Then what would be the definition of capital F? Remember, just compare these two right here, right? Compare these two. The definition of capital F, by definition, would be F of minus CD times the argument, right? So this is the actual mathematical relationship between little f and big F. Same thing for G. Okay? But anyway, in case you're interested in that kind of thing. All right. Now, let me do this. So I claimed that, these are both valid solutions of the wave equation. Let me just give you a very quick mathematical proof of it. I'll do it for form number one. Again, it's equivalent, as I just showed, to form number two. If you want to plug form number two into the differential equation, verify yourself, that's fine. But I'll just do that for form number one. Okay? So here's the wave equation. Okay, here's form number one, where it starts off with a z, right? Now, let's just compute both sides. What's the second derivative with respect to z? Now, just calculus. Okay? Now, calculus says, if I want the derivative of this term with respect to z, I'm going to put a prime on it. And then the chain rule says I have to go inside, take the derivative of what's inside with respect to z. But that's trivial. If I take the derivative of this parentheses term with respect to z, I just get derivative of z, so it's just one, right? So derivative with respect to z of this whole term just puts a prime there. I do it twice derivative, and just put a double prime there. Same thing happens with the g function, right? So it's just kind of trivial. Now, slightly more interesting, when I do the right-hand side, and I take the second with respect to time, again, now you really need the chain rule. So if I take the first derivative here with respect to time, I'll put a prime there, but then calculus says go in and take the derivative of this with respect to time. So what I put? A minus CD, right? If I take the second derivative, so one more time derivative, I put another prime, another CD gets factored out, so really minus CD squared, right? And the same thing happens with this, except you see it's plus CD, right? Of course, the minus doesn't matter because I'm squaring it, but anyway, minus CD plus CD. Now, anyway, so both of these terms here, look at these two terms here. They're exactly the same as these two terms, except there's a CD squared out in front, right? So the grand finale. Is this differential equation satisfied? This thing here is supposed to be the same as this thing here if I multiply by 1 over CD squared. Is it true? Yeah, sure it is, right? The 1 over CD squared just gets rid of this and gets rid of this, right? So yeah, of course it's true. Proof complete. That's a valid solution of the differential equation, right? And similarly, so would this be. You want to check it yourself. Okay. All right. Now, I kind of said a little bit in words already, but let's kind of show some pictures here. So here is a voltage described by the F function. Again, F is the wave going in the pot with a negative sign here. F z minus c dt is the wave going in the positive z direction. So let's say this is a pulse coming out of my function generator. Okay, a rectangular pulse. So, and on the line, if I have my magical camera and I take a picture of the voltage, you know, your magical camera that can see voltage, and I take a snapshot, that means I'm looking at what's going on as a function of z, but at 1t, let's call it t equals 0, I see this thing here, rectangular pulse. That's what the voltage looks like versus z. Now, what I do is I don't have an animation here, but have to use your imagination. Imagine I let time elapse now, starts from 0, goes to something called t1, which is a little bit bigger than 0. Then later time t2, a little bigger than t1, right? So I'm letting time elapse. What's happening? The pulse is simply moving down the line in the z direction, and it's moving at the speed of light. Because again, as time progresses, what's happening, right? At t equals 0, it's just a plot of f of z. So this is the same thing as this. At a later time, it's just delayed by what? CD times t. So if I'm at t1, it's delayed by CD t1, right? So this is the delay, right? It's been delayed. It's traveling. It's traveling at a velocity. So after a little bit of time, it's moved, of course, right? A little later time, it goes from here to here. But later time, it goes from here to here. It's not changing shape. On a lossless transmission line, signals do not change shape, right? They just move at the speed of light. Okay. And of course, that's wonderful for sending information from point A to point B, right? That's what we like. Okay. Now, if it's the G function, Z plus CDT, it's the same interpretation, just going in the opposite direction. So here it is, it's t equals 0. Now it's going in the negative direction. Okay, the absolute value of the distance traveled is again, speed of light times t, but Z is getting more and more negative, right? So at time t1, it's moved from here to here. A little bit later time, it's moved from here to here, right? So Z is getting more negative at the center of the pulse. But it's the same principle. Okay. All right. Now, here's an interesting note. I said there's no exact solution in the time domain if you have loss on the line. It can still be studied numerically, but there's no simple solution. But just for your benefit, let me point out what loss does. First thing is kind of obvious. If it's a lossy line, that could mean you have R or G or both. The signal is going to lose energy and therefore lose amplitude, right? That's kind of no-brainer. But also, kind of the worst news is that a lossy line causes signal distortion, which means the pulse changes shape, and usually sharp edges get blurry and the pulse kind of broadens out. So here's the pulse starting at maybe at the left end where the signal generator is, and you watch as it goes down the line. Now remember, if it was lossless, all you'd see is this, right? Just moving down, not changing shape. But here's a real life lossy transmission line. Now it's getting kind of blurry. It's losing amplitude, getting kind of blurry, even more so, right? So if you let this signal go long enough, it's going to be hard to recover it, partly because it's so small, but even worse, it can be unrecognizable because it's changed shape so much. And that's why in real life, people have to put repeaters every so often on a practical transmission line. So in a digital system, you have these digital pulses, but you want them to stay digital pulses and not spread out so much that they all interfere with each other and everything. So the repeater's job is to look at the signal, reconstruct it, and send it back again as a nice, crisp, sharp digital pulse, right? So that's what a repeater does for you, okay? Now, by the way, we're not talking about antennas yet. That's the end of the semester. But one of the nice things about a wireless system is if you have a wireless system with an antenna sending out a signal and another receive antenna, you're just propagating the signal through air or free space, and free space never causes distortion, right? But transmission line people have to worry about this. Okay. Now, this is really kind of going outside the scope of the course, but I'm just sneaking it in for your own benefit for those that are interested. I'm stealing some slides from the microwave engineering course. where we study numerically signals propagating on lossy transmission lines. And don't worry about how we got it. It's a Fourier transform method, but don't worry about that. Just look at the pretty pictures, okay? Here's a microstrip line, top view of a microstrip line fed by a probe here. It's going to launch a signal, which is a nice, clean, rectangular pulse. It's a pretty narrow pulse, and the time domain, the time duration is 0.5 times 10 to the minus 10 seconds, okay? So I guess that's what, 50 picoseconds. And don't worry about this, but that's all the dimensions we used for the circuit board and everything, the microstrip line. Okay, so from the numerical calculation, here's what the things look like. Now I'm plotting versus time now. So imagine I'm putting an oscilloscope, I'm taking an oscilloscope and connecting an oscilloscope to different points on the line and trying to see on the oscilloscope, what does the signal look like as the signal rushes past me at that point, right? Okay, so here I'm just 1 centimeter down. So my oscilloscope is attached, wherever 1 centimeter is, let's just say it's right here. So it's not very far from where it got launched. So it's already got distorted though, right? It's supposed to look like this. That's what it would look like on a lossless line. It changed into this, right? Look at this funny spike that's occurring. Now I put my oscilloscope a lot further down the line, wherever 20 centimeters is, and look at that. It's really getting distorted bad. Here's 100 centimeters, 1 meter, right? So you can see it's getting smaller and really distorting bad. That's the kind of thing I'm talking about. Right? Now microstrip is pretty lossy. It's got a lot of distortion, a lot more than something like coax. So this is like an extreme worst case, to be honest. But it emphasizes the point, though, right? Lossy lines can cause distortion. Okay. Coax are circuit boards. Now, anyway, okay. Any questions on that? Okay. Plug there for the microwave engineering course too. Really nice course. Okay. Anyway, taught usually every fall. Okay. Anyway, now the goal now is to solve for the current. Now, I just said the current and voltage, they obey the same differential equation, but they travel as a unit. When we say the signal, we mean both, coming out of the generator, right? Now, this wave going down the transmission line, it's got both voltage and current, and they're related to each other. And they're related by something that we're going to derive here in a minute, something called the characteristic impedance. That's what the meaning of characteristic impedance is, the ratio of voltage to current for the signal going down the line. That's what it means. Okay, we're going to bring this out of the analysis. All right, now here is the first telegrapher equation. I'm just going to keep it simple and assume it's a lossless line. All right, so get rid of the R term. We just have this. Okay, now voltage on the left, currents on the right. This telegrapher's equation is, of course, saying they're related, right? So let's see if I can somehow bring out this relationship better. Now, here is the voltage. Okay. F is the wave going in the positive Z direction. G is the wave going in the negative Z direction. Now, I need a notation for the current. Arbitrary what I call it, okay, but I called it U and V. So F and G are voltage, U and V are current waves. So U is the current wave going in the positive Z direction. V is the current wave going in the negative Z direction. So F and U go together. F and U, you're talking about a wave or a signal going down the line in the positive Z direction. F is its current, F is its voltage, U is its current. G and V go together. That's where signal going back, like from a load toward the generator, right? G is its voltage, V is its current. Okay. All right. Now I want to plug into the telegrapher's equation, so I'll need this simple calculus again. On the left, you can see I need derivative voltage with respect to Z. So take this equation, take the derivative with respect to Z. That just puts the primes here. On the right, you see I need derivative current with respect to time. So I start with the second one and take the derivative with respect to time. Like I just reviewed a second ago. That's going to put primes, but the chain rule says minus CD here and plus CD here, right? So I got these two things, and now I plug into this equation here. And here's the equation. So here's plugging in. The left side minus L times that derivative current. Okay. Now, the easiest way to proceed at this point is to compare similar terms. That's what I mean by equating like terms. Similar terms mean anything that looks like Z minus CDT lumped together versus anything that has Z plus CDT lumped together. Okay. So where do we see Z minus CDT? Well, I see it here, right? I see it here. That's this. Okay, what am on the right-hand side? Oh, I see it here, right? And that's this. And similarly, what about when I see something that looks like this? I see it here. And I see it here. That could copy down here. Okay. Now, so notice that this relates the U to the F. Remember, F and U go together, right? It's a wave going in the positive Z direction. But it says that U and F are related, just like for a wave going in the backward direction, V and G are related. Okay. Now, my goal is to solve for U and V. And you can see I'm almost done, but I don't really have U and V. I have U and V prime. So the logical thing to do is then just integrate both sides with respect to time. Okay. All right. So integrate here and integrate here. Okay. And lump these two constants together, take it across the equal sign, and then integrate. Do the same thing for this. Okay. Now, when you integrate the function of time, there should be a constant that comes down, but it's the same on both sides, so I ignore that. This is a function of time. Just like when you take the derivative, it comes out, and integrate, you divide by it, but I'm doing the same on both sides, so I ignore that. But anyway, so integrating both sides, you get these two equations right here. Now U is known in terms of F, V in terms of G. Now, mathematically, this is what the note is saying. Is like, oh, kind of caveat here. Calculus really says that whenever you integrate both sides like that, there should be a constant integration. Okay, constant with respect to time. But I'm arguing that that's going to be 0 here because any constant, which means constant with respect to time, would be a DC value, a DC voltage or DC current, and I'm assuming there is none. I mean, it could be. In addition to a signal generator being attached to the line, I could have a battery attached to it too. That's fair game, I suppose, right? Why would you do that? I don't know, but you could if you wanted to, right? But I'm assuming we're not doing that, right? So there's no DC values here. So you can ignore the constant integration. Okay. So now let's look at this term L times CD. Remember, CD can be written like this, 1 over square mu epsilon. Also remember that for any transmission line, mu times epsilon is L times C. Conductance impedance length times capacitance impedance length. Now, simple math, just rearranges this to give square root of L over C. Okay. Now, that is going to be defined to be the characteristic impedance, the symbol is Z0 of a transmission line. So Z0 is square root of L over C, and the units turn out to just be ohms. You can prove that, okay? But it's also because this relates voltage and current, as we'll see in a second. So the units of Z0 are ohms, but it's square root of L over C. Now remember, let me remind you that right now I'm doing a lossless line. There is no R and G, so it's only L and C. So Z0 is the square root of L over C. Okay, so that's these two constants right here. So putting that together, here's the U function and here's the V function now written in terms of Z0. Okay. Now, proceeding on, here's the current function. And now the U and V are the same as the F and G, but divided by Z0. Okay. Now, notice that there's a minus sign here. So the U and the F, wave going in the positive Z direction, does not have a minus sign. But for the wave going in the negative Z direction, there's a minus sign here that relates the V to the G, the current to the voltage. Okay, so don't forget that minus sign. That's important there. Okay, now anyway, so here's the complete current expression. Here's the U and the V from just a second ago. All right, so just plugging back in here, here's the complete expression for the current. Okay, this is just equal to this, and this is equal to this. So we're done. So summary. So in the time domain, for a lossless transmission line, this is the most general way to represent the solution for these waves going back and forth on a transmission line. Okay, the voltage and the current. Let me go over it one more time. Now, the notation is, CD is the speed of light on the transmission line, which is 1 over square root of LC. You can also say 1 over square root of mu epsilon. And Z0 is now a number that's called the characteristic impedance of the transmission line. Okay, it's a property of the transmission line. Remember, L and C are properties of the transmission line. So Z0 is a property of the transmission line. There's nothing to do with the generator or the load or anything like that. It's the property of the transmission line. So you got the voltage. It's a sum of two waves, one going down the line in the Z direction, one coming back going in the negative Z direction. The current is the sum of two waves, One going down the line in the z direction, one coming back and going in the negative z direction. So again, these two are a pair, right? F function, these two are a pair, G. So this is voltage. So these two right here go together. This is voltage and current for a signal going down the line in the z direction. These two go together, and these are the voltage and current for a signal going in the negative z direction. Now, here's the important thing in this physical interpretation. For a wave going down the line, the voltage of that wave, the voltage of that signal, is related to the current of the signal by the characteristic impedance. Current is voltage over characteristic impedance. It's kind of like a simple Ohm's law, right? But we're not talking about some resistor here. We're talking about the signal itself going down the line, but kind of the same kind of way you think. So again, current is voltage divided by characteristic impedance. Now, here's a very important thing you don't want to forget, and it's the second bullet here. If the wave is going down the line in the positive z direction, current is simply voltage divided by characteristic impedance. If it's the wave going in the reverse direction, don't forget this minus sign. The current is the voltage divided by Z0 with a minus sign. Might seem kind of strange, but as I'll show you in a second, it's perfectly natural. Okay, so let's go through that and then it'll become obvious. So here's a wave. I don't care what the shape of it is. Let's just say it's a rectangular pulse. A signal going down this transmission line, a coax, or wherever it is, right? Now remember, now let me remind you, I don't care which way the wave is going, this way or this way. We never change our reference directions for voltage and current. The reference direction for voltage is always plus on top, minus on the bottom. The reference direction for current is always on the top wire pointing to the right. Remember that? We're not going to change that. Now, okay, now you'll see this notation from now on very often. I put a plus superscript on a voltage or a current. That means it's a plus wave, a wave that's going in the positive z direction. The red arrow means it's going this way, right? Positive z direction. If I put a negative sign there, I'm talking about a wave going in the negative z direction. Now remember, for a wave going in the positive z direction, that's the F function, right? The F function. So here's the voltage, here's the current. Okay, so voltage over current, it's obvious, it's just this number, Z0. Okay, so voltage and current have the same shape. You plot voltage and current of the signal, they've got the same shape, just different amplitude, right? Related by the characteristic impedance. Okay, this plot I drew, why it could be a plot of the voltage, it could be a plot of the current, it could be either one, they have the same shape. If I put them on the same plot, of course, the current's going to be much smaller because you're dividing by the characteristic impedance, which is usually something like 50 ohms or whatever, depending on the line, right? Anyway, that's the forward traveling or plus wave. Now, what about the wave going in the negative z direction? And what about this crazy minus sign here? We'll see if that makes sense. First, it sounds kind of funny, but it actually makes perfect sense. Now, let me point out one thing that may be kind of obvious, but it's important. It's only one transmission line. The transmission line itself is perfectly symmetrical, like a coax or whatever. Or if it looks like this, it's a twin lead. But anyway, the transmission line is perfectly symmetrical, and the transmission line doesn't care whether the signal's going this way or this way. The physics should be the same, right? Because the transmission line is symmetrical, doesn't care, right? So whatever happens to the wave going this way should be identical to what happens to the wave going this way. Okay, now let's think about it. Look at this picture. So this voltage over this current is Z0. See the reference directions? This voltage over this current should be Z0, right? Now compare that to this picture, wave going this way. Remember, the physics is the same. So my claim is this voltage over this current should be the same, should be Z0. Is that just turning everything around, the mirror image, right? But is this current, this blue current with this reference direction pointing from right to left? Is that what we call I on the transmission line? No. The reference direction is always this way. That's what we call I, right? I'm moving the negative sign, just means it's going this way, right? This is what we call I on the transmission line. This is therefore negative I, right? So the physics is indeed the same. It's just a reference direction issue. So voltage for this negative going wave here called V minus, I minus, V over negative I is Z0, and therefore V over I is negative Z0, right? So it's perfectly understandable. It has to be that way. That's where the minus sign is coming from. It's nothing mysterious, just because of the reference direction. Okay, think about it for a second. Does that make sense? Okay, good. Oh, wait, let me. Yeah. Okay, let's do an example. So last time for the good old coax, I showed you RLGC. I derived 3 of them. I didn't drive the R, so that'll come later in the semester after we talk about the skin effect. But anyway, if it's a lossless line, there's no RNG anyway. Now I know a real coax in real life has an RG. I gave you the formulas for it. But if the RNG are small, usually people assume in real life that the RNG are small, and most transmission lines are pretty low loss, then you don't need to worry about RNG when you calculate characteristic impedance. Remember, I derived characteristic impedance assuming it's a lossless line. But my claim is if it's a real life low loss line, that's perfectly fine. Good enough approximation. Okay. So when people talk about the Z0 of a coax, they're not going to worry about RNG. They're going to assume it's lossless and just use the theory I just showed you, right? Okay. So from last time, here's the C, here's the L, right? Well, I just plug in, right? Here's the formula from a few minutes ago, square root of L over C. So just plug in, right? And just rearrange and simplify a little bit. Like there's 2 pi's that can be lumped together. So it's 2 pi squared, but then you take the square root and bring it out. You'll have a mu0 over epsilon 0. And then you can epsilon r downstairs. And then in terms of the geometry, we have a log here. This log comes upstairs, log squared, but then square root, so just log, right? So the final formula for the characteristic impedance of the coax is this formula right here, where I've taken the liberty to define what's called eta 0, the square root of mu0 over epsilon 0, very important number. We'll meet it all over the place later in the semester when we talk about plane waves. But anyway, that's called the intrinsic impedance of vacuum with free space. And the units are ohms. Okay. And an approximate value for it is this. People often just remember it as 377 ohms, the intrinsic impedance of free space, but here's a more exact value. Okay. Remember, let me remind you, mu0 is an exact number for all practical purposes, right? At least up until 2019, I guess. And here's a very accurate formula for epsilon 0. So, so that's how you would get this. So there's a formula for Z0 of a coax. Notice that the characteristic impedance, of course, it depends on dimensions and it depends on the material that's inside of it. Right? Now, it's really the ratio of dimensions that's important. Okay. So if I take a small coax with a certain A and B, and I take a much bigger coax where A and B are both 10 times larger, have I changed the characteristic impedance? No, I haven't. Okay, so it's the ratio of dimensions that determine the Z0. Now, I'm not talking about this today, but let me just say that an advantage of having a bigger coax is that it can handle more power. Okay, it has lower loss, so the wave will attenuate less as it goes down it, and it can handle more power before you get things like dielectric breakdown. So in your lab, when you connect a coax to the oscilloscope, it's probably still coax this big, right? It's not very big. If you look at those big coaxes running up, cell phone towers that are carrying a high power signal, they may be that big around, right? Really high power coax, right? So you can make it much more high power and lower loss by making it bigger, but that has no effect on the characteristic impedance, which is the ratio of dimensions that determine that. Okay, so that's a practical note. All right. And there may be a homework problem later. We have to design one, but simple problem. So if I give you its Teflon and the epsilon r is 2.1, and I say let's take an inner radius of A corresponding to some wire here, what would the outer radius B be in order to give you some value? Easy problem, right? You have the formula here. Now here's the popular twin lead. Now usually, like I showed you, the twin lead has a strip of plastic supporting the 2 conductors, but I'm ignoring that. So I'm assuming 2 wires in free space. I'm not deriving this. The derivative is a little more complicated, but here's the capacitance per unit length, and here's the inductance per unit length. One more time, if you multiply them together, notice that you can see L times C is mu times epsilon. Okay. Now epsilon r is whatever this material is that the wires are embedded in, But for practical twin lead, again, it's going to be epsilon r is equal to 1, right? Because it's just in air, right? But just to be more general, I left it there anyway. Okay. You can take it and plug in the formula for z0, square root of L over C. It comes out like that. This is the inverse hyperbolic cosine function. Okay. And now it turns out you can approximate the inverse hyperbolic cosine function in terms of just a simple log function. Okay. And that's a valid approximation when the spacing between the wires, between the centers, is much larger compared to the wire radius. You know, skinny wires, pretty widely separated. So when you see that one homework problem in homework 3, where it's talking about use the exact formula or the approximate formula, that's what it's talking about. Okay. Okay. So remember I showed you the other day some practical transmission lines. So these are the forms of the transmission line that you see in the TV industry, cable TV industry, coax and twin lead. Okay, and remember this is the twin lead strip of plastic there. Now there's industry standards for characteristic impedance. Okay, for coaxial cable in the TV industry, the Z0 is 75 ohms. Now, by the way, what's so important about this characteristic impedance number? We're really going to see that in note 7. But so I'll just give away the secret. When I have a transmission line coming down and meeting a load, the load could be a receiver, it could be your TV set or something. You want all the power, all in the signal going down the line to go smoothly into the load, right? Into the receiver. You don't want reflected energy because it's wasting energy, right? Not only that, the reflected signal might even interfere on the system or cause even damage if it's strong enough, right? You don't want reflections. As we'll learn in note 7, if the load resistance is the same as the characteristic impedance of the line, there's not going to be any reflection. And the signal smoothly gets absorbed in the load and no power gets reflected. That's why it's so important. All right, but we'll learn that in note 7. Anyway, so in TV industry, this is the standard for coax, and 300 ohms is the standard for twin lead. Okay. And sometimes, I mentioned this the other day, sometimes you want to connect coax to twin lead. You never want to just take a twin lead and just, solder it to the coax directly. Because then you're connecting a Z0 300 ohm transmission line to a Z0 75 ohm transmission line. And if you believe what I just told you, if the signal's coming along, let's say on the 300 ohm line, and it just hits a 75 ohm line directly, there'll be power reflected, right? So you want to have a matching transformer that changes the 75 ohm impedance to 300 ohms. So the signal coming on the twin lead thinks it sees 300 ohms here, right? So there's be no reflections. That's the job of this. It's a matching transformer. And in a later set of notes, we'll talk about the matching transformers and all that kind of good stuff. But not today. All right, anyway. Now, here's an important note, too. The TV industry is kind of an oddball. The TV industry, like I said, has 75 ohms as the standard for Z0 on their coaxes. But in the microwave industry, the standard is almost always going to be 50 ohms. So if you're a microwave engineer working on like a microwave coax in a microwave system, you're working on a transmission line like a microchip line or a circuit board, any kind of practical microwave work in the microwave industry, you're almost always going to hear Z0 equals 50 ohms. That's the industry standard in the microwave world. TV world a little bit different, 75 ohm standard, or 300 ohm for the twin lead. Okay. All right. Here's a few things about the microstrip line. This is what it is again. So one conductor is the strip on the top of the substrate. The other conductor is just this big old ground plane on the bottom, right? So you have current I flowing in one direction. The return current is spread out here on the ground plane, who's acting as the second conductor. That's microstrip line. If you make a very crude approximation, assume that the strip with W is pretty big compared to the height H, then you can treat this like we do in 3318 as a so-called ideal parallel plate capacitor and get a very simple formula for the capacitance. And you can also derive a simple formula for the inductance. You can do that based on Ampere's law. Or you can just say, hey, once I have C, I know L. The C times L is mu epsilon, right? That's the quick and dirty way to get L once you have C. But anyway, here's L and C. If you're willing to make that very, very crude approximation, and then taking square root of L over C, this would be the characteristic impedance, right? Now, in one homework problem, in homework 3, you're going to be asked to use a more realistic, more accurate formula for a microstrip line. And that's what it's talking about right here. Again, it's kind of borrowed from the microwave engineering course. Okay. And this is one of the most accurate CAD formulas that I'm aware of. Okay, so this is like a formula that I would use if I'm designing a real practical microstrip line. Now it's a CAD formula, CAD stands for computer design. CAD formula, it's an empirical formula, which means it's not derived. What it means is people spent much time, hours, days, weeks, trying to come up with an approximate formula that describes it, right? And after much experimenting, they came up with this formula right here. Okay. Now, this is a formula for, okay, let me go over everything. So W is the width. Epsilon R is the relative permittivity of the substrate. It's assumed to be non-magnetic. So mu is just mu zero. And H is the substrate thickness. Okay. Now, you can have a formula for Z0 if W over H is bigger than or equal to 1, and a formula if it's less than or equal to 1. I didn't bother to give you that because practically in microstrip design, if you're shooting for something like 50 ohms, it's almost always going to be true if W H is bigger than 1. Right. So I didn't even worry about the other formula. Right. Now, in this formula, you see something called epsilon or effective. What's that? Now, in a coax, all the energy going down the coax is confined between the two conductors and stays in the Teflon. There's only one epsilon, right? Epsilon of the Teflon. Now, here, if a signal is going down a microstrip line, part of the energy is in the substrate, part of it is in the air. So it sees an effective epsilon R. And that's what's called epsilon R effective. And there's no exact formula for it either, but here's an approximate CAD formula for it. Okay. Now, another thing that the formula has, and this is usually not worth worrying about, such a trivial, minor correction or improvement, but notice it actually has the thickness of the metal itself. So T is the actual thickness, vertically of the conducting strip. The strip is normally made out of something like half-ounce copper, which means it's like 17.5 microns in thickness, and that's small enough you don't have to worry about. Okay, but if you want a tiny, tiny improvement, you can actually add this term in there, right? Okay. And on a similar note, notice that here you don't actually see the width. Width, W is the physical width. You don't see this in the formula. You see something called W prime. And what is W prime? It's like an effective width. It actually counts for the thickness of the metal strip. Again, normally not worth worrying about, but tiny, tiny improvement. Okay, so this is really a good formula. Counts for the epsilon R effective. It counts for the actual thickness of the metal. Counts for everything. It's a really, really accurate formula. Okay, so that's the more accurate formula that the homework problem is going to be talking about. Okay, all right. Now, a few more comments about transmission line theory. We're about ready to wrap up this set of notes here. A few more comments here. First bullet says transmission line theory is valid at any frequency. I mean, any signal in the time domain, or if you're in the frequency domain, at any frequency, and for any type of waveform, as long as you have just nothing but a pure, straight transmission line running down. Now, transmission line theory is perfectly consistent with Maxwell's equations. Remember that calculation I did with the point vector? Okay, that's a typical example of that. Now, in transmission line theory, we derive the telegrapher's equations. So obviously, we work with voltage and current. We don't work with E and H fields, but they're there, of course. But we prefer to work with voltage and current because it's easier than working with the fields. But everything is consistent with Maxwell's equations. Transmission line theory is exact. There's no approximation. The telegrapher's equations are an exact set of differential equations. But transmission line theory is exact, even though it's voltage and current. Okay. Now, circuit theory that we learn in our circuits course is a really low frequency approximation to transmission line theory. So if you have your breadboard, for example, and you have two wires connecting this component to this one on your breadboard, in good old circuit theory, you don't think of that as a transmission line, right? You just think of just jumpers going from this hole to this hole, and that's all there's to it. Okay, you can think that way at low frequency, right? There's like in the frequency domain, there'll be a wavelength. Wavelength is C over F. And something like kilohertz, the wavelength is miles and miles and miles. So yeah, you don't really need transmission line theory. Same thing, 60 hertz. A power engineer doesn't really need this going across a substation, but microwave engineers do, right? So on a circuit board operating at 3 gigahertz, you really have to think that microstrip line coming out of this process or whatever, going to this component, there's a wave, right? There's a signal going out of the generator, clock signal, whatever it is, going down the line to reach this component. That's how you have to think, right? You can't think in terms of circuit theory. That's not valid anymore. Even for modern computers, everything is a wave now going on that circuit board, right? That's going to go down the line, it might reflect. If there's a mismatch between the load and the Z0, energy might come back. It might be multiple bounces. We'll do that kind of problem before too long. Okay. All right. Now, it's fair to ask this question. Is there any way, shape, or form in which transmission line theory is not exact? Does it ignore anything? Okay, and the answer is yes, to be honest, yes. Okay, here's what it ignores. Transmission line theory is perfectly valid, exact, for just a pure straight run of transmission line. Okay, but it ignores what you might call discontinuities, anything that deviates from a perfectly straight line. That can include bends or nearby obstacles. Here are a couple pictures that illustrate. Here's a coax. If it was a straight section of coax, the transmission line theory is exact. Okay, but what if I bend it? Okay, now I'm not changing it. Same Z0, same line, I just bent it. But that's a discontinuity. So if I have an incident wave coming from a signal generator, of course, I want it to go straight through, right? There'll be some reflection there. So I'll lose some energy, and only part of it, energy gets transmitted. That's a discontinuity. And that's why people recommend you don't bend coax too greatly, right? If you bend it a lot, you're risking this kind of discontinuity effect and might be a lot of reflected wave. You don't want to do that. Okay. Now, it's even worse if you have something like twin lead. At least here, all the energy is confined, right, inside the structure. I mentioned the other day, for twin lead, remember that picture, electric field is spread out. Rate decays pretty fast, but it's still spread out to infinity. So if I run something like a pipe or something near the twin lead, there's going to be interaction between the two. So there'll be an incident wave coming along, there'll be reflected wave because of that interaction. Even worse, because it's open, energy can escape, in other words, radiation. So if I put some kind of a pipe or something near this transmission line, not only is it a reflected wave, then there could be even radiation coming from this discontinuity too. I'm losing energy that way. So it's even worse, right? Now, yeah, you can minimize these effects. Remember, keep the wires as close together as possible, twist them to get like Cat5, right? That's how you minimize these effects. But it's never as good as the gold standard coax, right? So if you really want to reduce interference, that's the gold standard. Okay? No radiation. Still might be some reflections at a bend, but you can minimize that by not bending it too much. Make sense? Okay. Just for your benefit, a summary page. Summary page. All right. Any questions before I fire up note 7? Okay. Won't get too far, about 10 minutes left, but let me get a running start in it. Okay. Now, pulse propagation reflection, and reflection we'll get to not today, but next week. Okay. Now, first slide is just a reminder. You can write the waves like this, or you can write the waves like this. Okay, remember, the F means wave going in the positive Z direction, so I'll sometimes use this notation. It means I'm talking about this, or written like this. And minus means I'm talking about the wave going back in the negative Z direction. So it's the G wave. Could be written like this, or alternative notation could be written like this. Now, as I said in the last set of notes, this form here with the lowercase f and g is convenient for visualizing a wave moving down the line. Remember that rectangular pulse moving down the line? The uppercase f and g, this form is a little bit more convenient for looking at what an oscilloscope would display, because an oscilloscope displays versus time, so I like to bring out the time here, so t minus something. If I put an oscilloscope further down the line, Z is increased. So what is that going to do to the oscilloscope? Give me a delay, right? Time delay of the waveform on the oscilloscope trace. It's a more convenient way to think about oscilloscopes connected to the line. All right. So in this set of notes, I'll be using this the most often. In the last set of notes, I use this, but in this set of notes, I use this more often. Okay. Now, we'll get to reflections later in the notes. First, I'm not going to worry about that. And what I'm going to do for simplicity is just assume a semi-infinite transmission line. So there's a signal generator putting out a voltage, could be like a sawtooth or something, whatever it is. And that starts propagating or traveling down the line, but the line goes on forever. That's what these arrows mean. So naturally, nothing's ever coming back, right? Okay. And again, I don't always draw this arrow here. I did it one time here. Remember, I just draw this one usually, but that's the reference directions. Transmission line, semi-infinite, characteristic impedance Z0. Left end has a voltage generator putting out some waveform. It could be anything you want. I just choose a sawtooth to illustrate. Okay. Here's the general form that emphasizes I have a wave going in the positive Z direction, a function of Z and time. But remember, we know it can be written like this. So this is two different notations for the same thing. Voltage wave going in the positive Z direction. Okay. This illustrates kind of the functional dependence. T and Z are related. Okay. Anyway, let's see if we can relate everything to the generator. Because this is a generator sending out a known signal, like a sawtooth. Okay. Now, if I just set Z equals 0 in the formula, then the voltage of this plus wave, that's all we have on the system, a plus wave, there's nothing coming back, right? So the voltage at Z equals 0 has to be set Z equals 0 on the right-hand side, just F of T. Okay, now we also know that the voltage at Z equals 0, because it's connected right to the signal generator, has to be the generator voltage. So obviously the F function is nothing but the generator voltage. So this F symbol here can just be replaced by the VG symbol. So we've got a solution then for the voltage at any time, any Z on the line that's related to the generator voltage. There's the final formula. Very, very simple. Now it's got a very simple interpretation. Let's make sure we all agree on what the interpretation is. So at the generator end, where the generator is, Z equals 0, you've got this voltage called VG of T. Just imagine it looks like this. That's what's coming out of the generator. Now remember, we know from the last set of notes that no matter what a waveform looks like, it's just going to travel at the speed of light, right, down the line. So does this make sense? If I put Z equals 0, I just see VG of T, what's coming out of the generator. If I'm further down the line, and Z is like 1 meter, 10 meters, I still see the same generator voltage, but delayed, right? Of course, because it took time to get there. What time did it take? Well, distance, Z over speed, right? Of course, it's a no-brainer. It has to be that way. So this is what oscilloscope shows coming out of the generator. Here's what the oscilloscope shows if it's down the line at some distance Z. There's a time delay, TD, time delay. Distance over speed. It's almost no-brainer, right? Okay. Here's a little picture. Here's the oscilloscope. Hope you like my little cartoon of the oscilloscope. Oscilloscope attached to the generator, pretending it's sending out a sawtooth. Here's the oscilloscope, another oscilloscope attached further down the line. Same thing, but see the time delay there? Makes perfect sense, doesn't it? Time delay due to this term here. Okay. Now, here's a snapshot, which means we've got our magical camera. You know, a camera freezes everything at one instant time, right? This magical camera takes a snapshot at one fixed value of time and looks at voltage, which is now down the line. Voltage is a function of Z. In other words, the shape of the waveform on the line is a function of Z at one time, if we only had such a magical camera. Now, here's the interesting thing. Okay, it may seem perplexing at first, but it's actually very logical. So remember, the sawtooth wave is looking like this. It's ramping up time. That's a sawtooth. Now, if I plot in my snapshot, look at it, it's the mirror image. You see that? The ramp's going this way. Okay. Now, let's see if we can understand that. Okay, it's a mirror image. Now, it's got a different span too. Now, remember when I'm plotting in time, I'm saying the sawtooth has a time duration of, we'll just call it delta t, whatever that is, you know, microsecond, whatever you want it to be, right? It's got time duration delta t. Now, it's traveling at a speed, the speed CD. So during a certain time interval, it's going a certain distance, delta z, which is speed times time. So when you plot versus distance at a fixed time, you're going to see the span in distance being the speed of light times what the time span was, right? So that could be anything, depending on what the speed is, right? But anyway, but it's reversed too. It's the mirror image. Now, mathematically, the reason that is just look at the equation, right? So if I'm, let's say, at a fixed z, maybe z equals 0, and I'm plotting versus time, and time is getting bigger, I see VG of t. It's like the usual shape of the sawtooth, right? Now, what if I'm doing a snapshot like this, and I freeze time, you know, call it 0, whatever you want, but it's frozen, and now I'm changing z. If z gets bigger, what is this R given inside the parentheses doing? Time is fixed, but z is increasing, going this way. What is this argument doing? Getting more negative. So I'm going this way in the waveform, right? This way in the plot. See that? That's all it is. Okay. So yes, it has to be the image. Now here's another way to think about it, though. Here's another way to think about it. So now the oscilloscope shows this: the sawtooth coming out of the generator, but remember, there's this time delay, right? This time delay. Now visualize it this way. Again, I wish I had an animation, but just visualize it. The pulse in the, you know, on the line looks like this, the mirror image. Now it's moving at the speed of light. Now just visualize in your mind this thing moving and then sweeping past where the oscilloscope is. So which point sweeps past first? Ah, well, this point, right? We're at 0. And then a little bit later time, the middle sweeps past. So you see this. At the end, this part is swept past. So you see this, right? That makes sense? So if you visualize that, it makes perfect sense. This waveform, that's the mirror image, moving, sweeping past, is going to generate what looks like this. Makes perfect sense. So nothing surprising about this mirror image, right? Great. Okay, good. We're good on time here. Okay, a few more minutes. Here's another example. I mean, a sawtooth is good, but if you want to see another example, here's a case where you're putting out a step function. The voltage, the generator is putting out a step function, unit step function, U, the symbol. Now, by the way, I could leave that generator symbol. I could leave that generator symbol there, but if you're putting out, I'm sorry. But if you're putting out a step function, oh, wait a minute, I lost my place here. Yes, but if you're putting out a step function, another way to get a step function is just think of a battery and a switch, right? I can think of a voltage generator putting a step function, or I can just get it by a battery closing a switch. This is a simple way to think about it. But anyway, the voltage generator is putting a step function. So here it is at t equals 0. Later time, it's a mirror image. In time, it looks like this. So notice that on the line at a frozen time, see, it's going to be a mirror image. Okay, a little bit later time, it's moved. So this blue has moved down to the green. It's kind of, you know what it reminds me of? It kind of reminds me of like if you had like a big dam that was holding back a bunch of water, and all of a sudden the dam breaks. You're going to see this big head of water moving down the street or the road or whatever, right? It's kind of like that. It's like a voltage, head wave or something. So it's like this, and it moves down to here. And so notice that if you're an observer, I mean, same thing is with the sawtooth, but let's say you're here, an observer, you're not going to see any voltage until the waveform sweeps past you, right? Now, with this step function looking like this, it's all or nothing. You see nothing, and then as soon as it sweeps past you, immediately the observer sees, the voltage jumped up to V0. Because now it's swept past you, right? So it's not much of a complicated waveform. It's really 0 or it's the full voltage. So kind of like an interesting kind of thing. Almost like a water wave suddenly sweeping past you and the water suddenly jumps up. The steady state voltage would now be like this. So this is what is happening in the time domain. This waveform is moving. And so at the green time T2, all observers up to this point would see a voltage on the line that's V0, and all the observers on this part of the line after this would see 0. But then as soon as this green, keeps moving, and it's gone past you, everything's going to be V0. So it's steady state, infinite time, all the way out to infinity, literally. It's going to be the battery voltage, right? Which makes perfect sense, right? You have a battery, a switch, you close it, you wait long enough, it's going to be V0 everywhere, right? Makes sense. But see, it took time to reach the observer. It's kind of like flipping a light switch. You may think the lights are coming on automatically, but no, there's a wave. It took some time to get there, right? It just happens so fast you don't see it, right? But a oscilloscope can see it, right? It took time to reach there. Okay. All right. So this is a good place to stop. So next week we'll pick back up here, and now life will be more interesting because we're going to talk about a practical system with a load at the end and reflections. Okay. So go to your head, please do so. Okay. All righty. Thank you. And if anybody has any questions, I'll stick around as usual for office hours. We can meet here if you want.